Okay, so today is not really going to be a lecture, but more of a seminar of the work that we have been doing in Rome in the last 10 years, let's say. But I will try to stress during this seminar all the points which can be better understood if we have learned the previous two lectures. So I'll try to make contact with what I've told you the previous days. So as you know, we do a lot of computational and theoretical work in Roma, and in particular in the last years on this patchy colloidal particle, colloids of new generation, colloids with directional interactions. But today, I will try first to introduce these models and the interesting things that you can do with this type of models. You will see how entropy plays an important role in this class of materials. But then I will also try to show some results which are based on a simple experiment that in principle can be done in any lab with a little bit of expertise that try to really create this system that we've been studying on the computer just using particles made with DNA. So particles completely built with the DNA sequences, short sequences of DNA. That's the idea. So I will first review this concept of limited valence. We've discussed a little bit about this in previous days, the concept of equilibrium gels. Then I will discuss how can I design, so this is more a kind of material science approach. How can I design a material that become harder on heating? And then, again, you might already resonate with what I told in the previous lecture. How can I make a gel that is able to swap? In the first part, I will discuss simulation, and then I will show how can we do these things with experiment in the lab. Okay, so let me start with why are we interested in these limited valence particles and why we want to study them. And this goes back to the problem of trying to understand we started by approaching this problem, trying to understand what happened to the glass transition when we go down in temperature. Now, we've seen a lot of talks in these weeks about what happens if I compress my system at high temperature, hard sphere-like, right? And then, and there's a condition, the system loses ergodicity and transforms itself in a glass. But we have also discussed the possibility of approaching the glass transition on cooling, so being dense, but decreasing the temperature. And then again, you meet the glass transition, and you might find, even in temperature, similar features to the one that you've seen increasing the packing fraction. But you would like to see what is the lowest temperature that can allow you to form an arrested state. And if you try to do it with a spherical interacting particle, like an R sphere plus some attraction, you always end up in a gas-liquid phase coexistence. The gas-liquid phase coexistence is very wide. Interaction is isotropic. You know that the particle like to be surrounded by 12 neighbors. And so the density of the gas coexisting with the liquid usually is very large. It's larger than the density that you would expect for a glass transition. And indeed, this idea was already studied a long time ago by Shrikant in this article on Lennard-Jones system, where he studied theoretically and numerically in the intersection between the glass line, you see here, and the spinodal, the gas-liquid spinodal. So in some sense, he was able to detect what is the density, the lowest density at which you could, in principle, form a glass in this Lennard-Jones system. So there would be no possibility to form glasses, homogeneous glasses, let's say. You can always get phase-separated configuration in here, but homogeneous glasses for density lower than that. And at the same time, you cannot answer to the question, how can this Kaufman line, how this glass line end up if I go to lower densities? So we started this project with the idea of how can we design an interaction potential in such a way that we somehow suppress the gas-liquid phase coexistence. We started by studying these patchy colloidal particles. So particles, you can think of these particles as a simple hard spheres decorated with some attractive spots. So when the two spots are close by, closer than some cutoff distance that you can fix, it's going to be like an angular square well interaction, let's say. Then those two particles will form a bond between two. And you can continuously tune the number of patches that you put on your sphere. You can go from 5 to 4 to 3, and at the end to 2. We discussed the case of 2, the equilibrium polymerization case in the previous lectures. So let's see what happens if we do the calculation of the gas-liquid phase coexistence in the case of particle, let's say, with 6 patches. Nothing really changes. You see the density of the liquid coexistence with the gas, it's rather high. 50% of the volume is occupied with particles. So it's already a dense state. So there is not much we can do here. But we can go to lower values, from 6 to 5. You see already a significant decrease. You see that critical temperature goes down, the critical density goes down, and you see that the density of the liquid coexisting with the gas shifts on the left. You can keep doing this. We can go to particle with valence 4, particle with valence 3, even with particle with even smaller valence than 3, if you start to play with binary mixtures of particles with different, I don't know why this happens. Coming back. Even with particle with the mixture of particles with the valence 3 and 2, then you can even make it, you can bring this critical temperature to 0 and the critical density to 0. So in some sense, you can completely suppress the phase separation by decreasing the number of patches in your system. And this is how, for example, how the phase diagram of a mixture of average valence 0.05. So really a lot of particles with valence 2 and a few particles with valence 3 mixed together. And if you do that, then the phase diagram shows these gas liquid unstable regions, a packing fraction which is smaller than 0.01%. So really empty liquids. We've seen this, we have introduced in the previous lecture the Floris-Stockmeier clusters. And those are the lines that you see shown here, compared with the simulation. You see the agreement, how good is the agreement, even close to the percolation transition. So they're really a nice description of those clusters based on the theory that we have discussed that maximize the number of different cluster types. So the system is essentially composed by a non-percolating phase, a percolating phase, and then a gas liquid in the percolating phase. Of course, this line is just a geometric line because there is a dynamics, the bond breaks and reform. It's a system that you can equilibrate. You can do easily simulation down to this low temperature. So this line doesn't really mean much. I don't think it's this one. And this is how the system, for example, looks like if you want to think of what is this liquid that coexists with the gas at very low density. It's really a gel, what you have in mind as a gel. It's a chain of bifunctional particles connected with branching points, which are three functional units. So you can really provide a very nice description in terms of statistical properties of the network. You can count everything theoretically, the length of these chains, all the branching point, the size of this class, everything. We have a complete understanding of these materials. But the important thing is that now we have gone from this phase diagram that you see for isotropic potential to this phase diagram here, where you have this gas-liquid phase separation on the left and still the glass on the right. And now you can, in principle, access the glass. You can see how this line ends and how is the physics of this peculiar point. I will not discuss this. I like to discuss more on the fact that now we can go to very low temperature without in an homogeneous way, without encountering the phase separation, something that is impossible with isotropic potential. And in this region here, I'm trying to convince you that what you have is a liquid which is essentially a network controlled by the bonds and by the lifetime of those bonds that you can control with temperature. So if you go to very low temperatures, you're going to have very long-lived bonds, and you have a very stable network, and if you raise the temperature, then you start to break those bonds more quickly, more frequently, and you have a system which is more typical liquid-like. So this is a dynamical arrest, which I like to call of the gel type that you see here, which is conceptually different from the one that you have discussed this week due to the excluded volume, which is the typical one of a glass sphere. So in some sense, this is why our sphere is so important, because they are really the model for packing. And the this kind of limited valence models are the model for networks. So there are two extreme classes of materials that we can have. Physical jets do not only refer to patchy particles. I mean, you see these things also in atoms and molecules. Because there is some kind of universality in this valence. I mean, all systems which have the same valence more or less behave in the same way. They have the same type of phase diagram. You have collected several models that have been studied of particles which can form 4 patches or 4 bonds. And I put together also silica, PKS silica, 2 models for water, ST2 and SPCE. And if you scale the density according to the nearest neighbor distance, so that now everything is controlled by the same unit, then they are all very similar. They're all exactly, those are soft matter type models, and those are atomic models, and they are really very similar. Those lines that you see here are lines where the diffusion coefficient is the same, and there you see in this phase diagram they are quite flat. That tells you that density doesn't really play an important role, and the dynamical arrest is essentially controlled by temperature. Why is this happening? If I do this, it works again. No. I don't think. You mean the computer could go use it too? I didn't check. Anyway, let's see for an experimental check of these ideas. This is a clay, a soft matter system, so it's a small particle, platelet, which has charges of 2 different types. They are positive on the rim and negative on the surface, so that they prefer to form bonds of this type, T-type bonds. And in some sense, those particles can form a limited valence number of contacts. You can simulate this with this type of model, very simple model, and you recover the same physics of limited valence particles. Tell me. I'm trying to say that they are the same. I'm trying to sell the idea that they are exactly the same. Break and reform, unless you go to low temperature, and then the lifetime of those bonds gets longer, and then, but it's exactly the same. I mean, it doesn't really matter if they are patchy particles or hydrogen bonds. The physics. No, physical gel of this type, equilibrium gels. I mean, this type of gel that you can create in equilibrium because you've moved the phase separation out. And you have moved the phase separation out because the valence is small. So, for example, colloidal gels, they don't qualify. These depletion gels don't qualify. Yes, so physical gel is not the right word. I should say equilibrium gels. Sorry, it's a slip. Okay, so let's see this system here. If you do experiment, what you see that if you prepare these samples and you let it wait for months, then it phase separate. A phase separate at very low concentration, see here, less than 1% in weight. You can rebuild the density of the 2 phases by estimating the meniscus position, and you see that the density is exactly the same, which means that it's a phase separation between 2 phases which have the same properties. You see that the system starts from a fluid, and it becomes a gel, and then separate in a gel and in a fluid phase. If you look at how the structure factor evolves in time during this process, you see that 2 different behaviors. In one case, you see a continuous increase at low densities below this concentration here, that is the concentration of the gel in equilibrium. Then inside here, you have a spinodal decomposition type process. The structure factor goes always in time, and whatever you can do, it always keeps going. Instead, when you work on the sample at this concentration here, then it saturates, reaches equilibrium, and doesn't really evolve anymore. Of course, this is not a system where we control the valence. It's selected by the type of interaction, but seems to satisfy this type of physics. Let me show you 2 other systems. And now probably you don't know the dark side of Professor Charbonneau, which is his work on Pachi colloids. So here you have a nice application of Pachi colloids. This is the squid lens, and the squid lives very deep. The lens has to, so for pressure reasons, the lens has to be very flat. At the same time, you need to correct for the aberration that a flat lens produces. And so you need to build a gradient in the refraction index in your lens, in the lens of the squid, if you want to correct for this aberration. And nature does it by generating gels of different density inside the squid. There are gels which are very low densities. How can we do it? We can do it with proteins which are very directional, which are very directional. And so this group in Philadelphia, Alison Sweeney, has been able to do all the biological work, look at the molecules which are expressed, look at the scattering of those molecules, and realize that particles which are at the outside of this lens, they form object with valence 2, and then particles which are inside form much more compact structures. So you go from 2 to higher valence. So there is nature has selected the proteins in such a way to use this colloidal physics of the low-density Pachi particles. And more recently, the same group has reported also another system, biological system. This is the Pidan. This is the century egg that people eat in China. Those eggs, they keep the eggs for a very long time until they form this gel. It is due to some chemical that enters in the egg. And this is how they look in a Chinese restaurant. And these gels that they form in this century egg, is also similar. You see a phase separation process of very low density, less than 10% in packing fraction. There's a coexistence between these two phases. And again, if you plot the data, you show that there's a real physical separation between two different phases. And again, such a low value of density in equilibrium can only indicate a limited valence systems. So those are all in fact evidence. They are very, very nice, but we need the good one, the one in which we can control the valence and really prove it, and we will see this later on with the DNA. Let me go to the second topic that I want to, theoretical topic that I want to discuss with you, gelling on heating. So I want to create a material. Be done? Century egg is the Chinese name for century egg. Gelling by heating. So I want to create a material that this time gels on heating. So we know that if we go down in temperature, we might realize a gel. We've seen it. We just need to take a Pachi particle with more valence. But we want to do the opposite. Now we want to start from a fluid phase at low temperature, and we want to warm up and enter in this gel phase. So we want to sandwich the gel between two fluid phases. Of course, at high temperature, will be a gas phase, but we want to have a gas or fluid phase also at very low temperature. So how can we do it? We have discussed this physics here, the physics of the dipolar Hart spheres, the importance of the entropy, the importance of a low energetic ground state, which is unbranched in some sense. So we want to use now same type of physics, same type of ideas, and we want to, in some sense, control the average valence in the system with temperatures. So let's, now that we have better understood this concept of the phase diagram for different valence, what we would like to have is a system in which the valence changes with temperature, so that, let's say at this temperature I'm here, I lower the temperature, the valence goes down and I move here. I lower the temperature, the valence goes down and I move here, and so on and so forth. And so we will have this phase diagram saffron-like, in which the liquid goes back because the valence progressively goes down. So how can I design this system? A particle which changes valence by itself and go, let's say, from 4 to 1 or to 0. I can do this. I can say, okay, I have my particle with valence 4, and then I can transform this particle with valence 4 in a particle with valence 3 just by attaching another particle on it, capping one of the bonds, right? And then I can transform this particle, which is valence 3, in a particle with valence 2 by capping 2 bonds. I can transform this in a particle with valence 1 by capping 3 bonds, And then I can even transform this in a particle valence 0 by capping all the bonds. So I have to find a way of attaching those particles, red particles that cap the bonds, as a function of temperature, in such a way that at low temperature, this is going to be this stable phase, right? The ground state. Because I want to, at low temperature, to have a valence at 0. So for sure, I can play with the energy of the interaction between the red and the blue particle, make it stronger than the interaction between blue and blue, and gain, and make sure that at low temperature, this is going to be the ground state. Like in Safran model, the dipolar chains are the stable ground state. So what I can do, I have just to compare this energy here, the energy of forming a bond between two blue particles, with this energy here, the energy of forming a bond between the blue and the red particle. And if I satisfy this relation here, I'm sure that at low temperature, this is going to be the stable state. And so I'm sure that I input in the system the physics that I want, that there's liquid, fluid, at very low temperature. It's going to be a gas of those particles. Now, of course, I have to be also very careful that I don't want to have PP bonds. I don't want the red to be able to bind to itself. Because if they do it, then the ground state becomes the dimers of red and the networks of blue. Because that would be the ground state in that case. So if I satisfy this relation, then at least I know the ground state. And now I need to design the interaction between the red and the blue particle in such a way that at a finite temperature, this interaction takes place. Again, remember Safran. We want to have this, stabilize this, which has a higher energy state, and we have to do it increasing the entropy. In this case, in the number of points where you can attach the particle there. Let's see how can we do it. Now, if you remember my last lecture, if I have two particles which bind to itself, we have derived this expression, and we have seen that the bond probability, the probability to form a bond between these two particles, is related to an entropic term, which is the ratio of the bonding volume to the total volume, and an energetic term, which is the energy scale of the bond. So this energy we have fixed already. We are fixed by this inequality over here. Now we have to fix, we can fix this entropy, and make sure that we have the blue-blue binding like here, and then the red-blue binding a much lower temperature and much sharper, right? This is the idea. We want to first, if we come from high temperature, form a lot of blue-blue bonds, and then when we have very low temperature, we want to have a lot of red-blue bonds. We have to play with the entropy. We have to find a way to increase the entropy in this, so this means this bonding volume in such a way that this becomes the most stable state. And one way of doing it on the computer, that's, on the computer it's easy. I can control this bonding volume and I fix everything I want. So on the computer I do it, and I get this type of, when I solve the equations, in this case again Wertheim theory, I get that the blue-blue bonds now form, reach to 90%, and then they go down to 0 when the red-blue bonds start to become very intense. The number of blue bonds goes to 1. So this seems to be the right ratio parameter that we have picked. So we can do simulation for this ratio parameter and see if these theoretical predictions are verified. And this is what we find if we do the simulation. This is the phase diagram, first of all. And you see that this has exactly the shape that we expected. This has a re-entrant phase diagram. The average valence goes from 4 when we are here, and then goes to 0 when we go to very low temperature. So if you go now, those lines that I show you here are lines of equal diffusivity. And so from here to here, you go down in mobility a factor of 10, another factor of 10, another factor of 10. So the system gets slower and slower and slower, gels, and then gets faster and faster and faster, it becomes fluid again. So on the computer, everything seems to work. You look at the diffusion coefficient, it starts this temperature is on this axis. So it starts from a low temperature here. So let's go from high temperature. It starts from high temperature, it's very fast. Then it becomes slow, slow, slow. This is 4 order of magnitude slower. And then it starts to go back again. And this is the value that you would predict just for a precise gas of flower that you expect. So you go back to this value there. So that's exactly what we want. The system DNA material application, it's NetSeeman, so I really need to show him because it's really a brilliant idea. It was almost 30 years ago that he had this intuition that one could use DNA not for genetic or biological application, but for building materials. And the reason is that you can use this ability of DNA to control the association process between the bases. And so, in some sense, you can design the type of interaction that you want to have in the system, just by selecting the sequence of DNA. So the important sentence that I really like to stress is that the exploitation of DNA for material purposes presents a new chapter in the history of the molecule. And if you look on the web at the explosion of works that have came out from this intuition, is really impressive. What you can do today, it's really incredible. You can use this DNA not only to start very simple construct like this nanostar that we will discuss later on more, but you can build cubes, you can build vessels, you can build boxes, you can even open and close the box. And this is everything on the nanoscale. You can control just with other pieces of DNA. You can make tubes, you can make carpets of different types. You can address every point on the carpet the way you like it if you want. You can make crystals. Really amazing things that you can do. If you want to read more, you can go to this article, but there are many review articles because it's really an exploding field. We will use the simplest of these constructs that were imagined by NetSeeman, and I'm going to use this nanostar, the DNA nanostar, my hero. This is created simply by 4 DNA strands, roughly of 45 bases, each the red strand, the blue strand, the green strand, and the purple strands. And those strands are selected in such a way that they are going to form double helixes in this region here, in this region here, in this region here, and in this region here. And so here you see a representation of these DNA nanostars. In the centers, you see that I've selected A or A. So in this way, they will not form bonds and give some flexibility to the central core. So this particle can really move, all the arms can move almost independently. The sequence, as we had discussed the other day, is a palindromic sequence, a sequence that we put at the end. These spaces that you see here coming out. This sequence here is a palindromic sequence, and so this can bind to any ends of any other particles. Important thing is that the strength of interaction depends on this choice. So if I make a different type of particle, let's say valence 3, valence 4, valence 5, and I use the same strength, the same sequence in the sticky part, those particles will interact with the same energy. So I can create bulk quantities of these particles, all of them identical, and all of them no polydispersity, and all of them interacting with the same strength. So I can control the strength, and I can do much more. So how does it work? This is, you go on the web, you type the sequence that you want, you pay with a credit card, you wait 3-4 days, and then you get the sample, the powder in your lab, you mix it with water, a little bit of an NaCl solutions in the right proportion, and then the system does it by itself and you go down in temperature from 90 Celsius, this is roughly 80 Celsius, and the particles self-assemble in your sample. So now around 70, 80 Celsius, you have an Avogadro number of these particles. You can really do a lot. You can really do collective properties of this system, because you have many of them. People is trying to do patchy colloidal particle. In a few years, they will really, there are a lot of beautiful examples already, but most of them are limited to small quantity that you can just look on them under the microscope. Not sufficient amount that you can do bulk studies. There are a few exceptions. One is Granic that we discussed the other day, but this is really a powerful way of creating patchy colloidal particles. So high temperature, you have your isolated strand, your nanostars at the middle, and then at low temperature, these sticky ends bind. This is the epsilon that we have discussed before, and they form our network. So now we can control the valence, we can control the strands, so we can really check the theories. So we can make, first of all, we can check that we have this particle. You can do neutrons experiments. in your solution. This is the form factor of the particle that you calculated theoretically, the red one. The blue points are the experimental data. You see how nicely they match. Only a very small vector, there are some error, some differences, and they come from the fact that particles are charged, so there is some residual interaction due to electrostatic. Apart from that, the agreement is very good, and this tells you that you really have bulk quantity of this material. Okay, now we have them, we can use them. Let's see how we can, the test that we can make. First of all, let's test this idea that the valence is controlled, that the phase diagram is controlled by the valence. Now, compared to the previous experiment, now we are selecting the number of bonds and we are selecting the strength of interaction. So we have prepared DNA nanostars with valence 3 and DNA nanostars with valence 4. We have prepared the sample and studied in temperature concentration the phase behavior. And what you see is that at high temperature, the system is homogeneous. And then if you work at low densities here, then when you put it down, you phase separate in a gas phase and in a dense phase of DNA. You can measure with CT or with absorbance the amount of DNA, so you can plot the concentration of the DNA that you have in the sample at resistance in the gas phase and in the liquid phase, and then you can rebuild the phase diagram. And you see exactly what we have seen in the simulation, that the critical temperature goes down, that the critical density goes down from here to here, and again that the liquid density of the liquid coexisting with the gas shift and move to the left on decreasing the valence. So this is really the first, I would say, the first careful test, experimental test of this idea that the valence controls the phase diagram. And the system, it's a real phase separation. I mean, if you go here and you look at the fluctuations, you can measure with light scattering, and those are the results at different angles. And the lines are what you would predict for a critical phenomenon. This is very close to the critical point. This is a Lorentzian function. And you see how nicely the data are described by the theoretical expression that you expect to have close to the critical points. You see the divergence of the scattering intensity at all temperatures. Now we can look at these equilibrium gels. So now we can prepare our sample outside from the phase separation. So we can go here, for example, density larger than the phase separation. And then we can measure with dynamic light scattering density correlation function, the same correlation function that we've been discussing all this time. And this is the result that we see. And I want to stress the difference with the glass phase. You see that there is a plateau, there is an alpha relaxation, exactly like in glasses. But you see that the plateau goes up and grows with cooling. There were not many experiments of the behavior of the density fluctuations on a gelling system. But one that I want to remind you is the one, again, of the system we discussed in the previous lecture, the telecalic polymers, right? Again in Montpellier. And this system has a very similar behavior. You see that the plateau height goes up. Now you are increasing the number of polymers that we put in the system, the number of bonds that we put between the oil droplet. We see this increase of the plateau. Now here, the decay of the density fluctuation comes from the fact that the head of the polymer evaporates and find another droplets where to go. And this is a time which is always the same. It does not depend on temperature. So the alpha relaxation time is always the same. In our case, we have a DNA-DNA bond that controls the strength of the interaction between the particles. And this bond becomes stronger on cooling because there is a free energy of binding due to the sequence of the DNA. And so our system becomes slower and slower on cooling due to this increase in the strength of the bond. So we have both physics, the physics of the formation of the gel, and then the lifetime of the bond gets longer and longer, and the controls slow down the dynamics, the alpha relaxation dynamics. Yes. No, this probably, I mean, this is the one, when we reach 10 seconds, we are really at the limit of what you can do with this light scattering experiment, so I don't trust it too much. One should go to a new technique where, like a DDM, where you can go to longer time and see this type of things. But with light scattering, I would not be confident too much. these things are really equilibrium gels. I mean, things that you can cycle back and forth in temperature. You always find the same correlation functions. You can go on cooling or on heating. You can quench directly to the temperature. They're really equilibrium structures. You wait 30 minutes, and then the system go always to the same configuration with the same resulting correlation function, the same scattering profile. So it's really equilibrium system. There are a lot of interesting physics that we've seen with this system. First of all, this is a network, right? And the networks, we know that they are strong class formers. So the typical correlation time grows in an Arrhenius way. And here is the alpha relaxation time, plotted as a function of 1/t. You see how nicely it behaves. So this is, if you like, it's a colloidal analog of a strong class former. Again, it's not a coincidence. All of them are limited valence systems. In all of them, the lifetime of the bond is controlled by the energy of the bond. That's the only relevant energy scale. It's different from the case of Hall spheres or glasses, in which energy change, the activation energy changes with temperature. There's another interesting physics that we have found, which is the fact that if you look, so this was the temperature dependence of this. If you look at the Q dependence of these characteristic times, we find out, and remember that the light probes, the particles are 20 nanometer. The light is 400, 500 nanometers. So it's really, you look on very large distances compared to what we do in glass physics, where we look at the cage. There is a low temperature. You see a nice, very clear Q independence of the alpha relaxation time. So the alpha relaxation time is constant with Q. That's not what you would expect. I mean, think in terms of, okay, a small Q vector, I go to the aerodynamic type of prediction, that would be Q to the -2. Here you see, yes, you see the Q to the -2 as very small Q, but you see a large region of Q vectors where you see a constant value. We have studied this. If you're interested, you might read this article, but let me show you some recent results where we had seen, okay, but no one has ever looked at these things in simulation for systems. So let's try to look at the atomic and molecular system. You look at water. Those are simulations with millions of atoms for a very long time, but you can still do it nowadays with the graphic cards. And you calculate the correlation, the collective correlation function. Again, this is distances much smaller, much larger than the nearest neighbor distance. And you see that the alpha relaxation time is always the same for all curves. And here, this dashed line tells you the self, which this is a clear indication that the collective relaxation decay faster than the self, which means that they decay without particle diffusion. It's a process of decay of the density fluctuation which doesn't require transport of mass in the system. And you have seen this at different state points. We've seen this also in silica, decay as silica. We have simulated different densities, different temperatures. You see that the alpha relaxation time for all wave vector, again, those are quite large systems. They behave all in the same way. I like to explain this very quickly by saying that we have always to remember that density is a ratio between number of particles and volume. And so if you cannot decorrelate by changing the number of particles, you better decorrelate by changing the volume. And indeed, this is what is happening. Those are decorrelation associated to the propagation of the normal modes of the system. The oscillations in the system, elasticity fluctuation that propagate the system and decorrelate correlation functions. And of course, at a certain point, you will cross to hydrodynamics, but if the alpha relaxation, if the system is glassy, this crossover will be of extremely small Q. Close to the glass transition, this crossover will be of the order of meters. See this crossover, the real hydrodynamics. Okay, but let's check also our beloved Cobb-Anderson model, and that's different, completely different. Here, the alpha relaxation time scales with the Q square, the density. That's very clear Q square dependence. And if you think why this is happening, this comes from the fact that, wake up. This is our beloved Cobb-Anderson model, right? You cannot miss it. the Q vector dependence for this, it's remain Q square. And that's, it comes from the fact that now you don't have only to decorrelate the density, but you also have to decorrelate the relative concentration of the particle. This is a binary mixture. And again, this is interesting in respect to what Ludo has taught us. You need to equilibrate the concentration fluctuations. And if you want to equilibrate the concentration fluctuation, you need to diffuse the particles. There is no way you can eliminate a fluctuation in concentration without moving actually the particle from one point to the other one. And so this goes with Q to the minus 2. Now, this is also interesting for simulations because if you really want to study a big system with a binary mixture like this one, you better be careful because it would take a huge amount of time to really equilibrate. It will be almost impossible to equilibrate like a 1 million particle binary mixture Lennard-Jones if you want to be careful. Because there is a characteristic time that goes with Q to the minus 2. You really have to wait until all the small q have equilibrated. So this is the slowest time in the system. It's not the alpha relaxation time of the peak. This is the slowest relaxation time that you have in the system. We have also to be careful to look at this type of things. Okay, liquid more stable than crystal. We have alluded to this in my talk. I can only tell you that these DNA gels, at least on the computer, in the lab, they never crystallize. You can prepare the sample for weeks, and then it stays there actually for months. It stays there. It does not crystallize ever. On the computer, you can calculate the free energy with this Frenkel-Elad type of methods for the DNA gel, or you can do it for the DNA crystal, and you can show that the free energy of this very flexible Apache particles is really lower than the free energy of the crystal. So those are the gel is the thermodynamically stable state in this kind of system. Okay, so let's go to the last two things, gelling on heating. How can I create a gel that is cupping idea? So I need to cup my sticky sequence. So I need to add another particle. So I need to add something like this. But now the problem is that I told you that this sequence here is palindromic. Right? So if I add the complementary to that one, will form a PP pairing. Right? And so that will not be the right solution because we discussed that this PP should not be there. And then I have this problem that I want to increase the entropy of forming this bond. So the way we have solved this, excuse me, the way we have solved this problem was to make a little bit more complicated sticky sequence, which is this one that you see here, in which you still have this palindromic part, which provide the blue-blue binding, but then we have added some bases here and there that are not involved in this blue-blue binding. And then we have added in solution not one, but two single strands of DNA, short single strands of DNA. The red sequence and the green sequence. Why does it work? Let's see if I can explain you how it works. So let's look at the blue-blue binding. So this blue binding will take place through this space. You see that those bases are not complementary, so they will not form any bond. So there will be 8 base pair associated to this binding over there. But now I have also the possibility to put the green here and the red here. And in this way, I shield the blue, so the blue will not be able to bind to anybody else anymore. And now this interaction here is controlled by 12. So the energy of this interaction here is going to be lower than that one. And this is graphically shown here. So I have 2 pieces attached, one here and one there. So I created my isolated nanostar. So this idea of splitting the cupping sequence in 2 parts, it also adds an additional amount of entropy, which was we wanted, right? Because now we have to freeze the center of mass of 2 particles to create the bond. So it's even more entropically costly. So this is good because this destabilizes this binding, and only at low temperature this will take place. Now you use this theoretical software that has been developed for DNA. You can type in the sequences, and it tells you the temperature where you expect to have these sequences to bind. And so you can do the theoretical calculation, and you see that these blue-blue bonds behave like that, as we wanted, and the blocking bonds attach in this way here. So Above 40, we will have a gel, according to the theory, and below 40, then you will have the blocking that start to form, and then the gel that start to melt. And if you compare what the results of the simulation that we had, it's really very similar. Actually, it's even much better if you think about it. Look at the temperature scale. Here you go, to see this process, you have to go a factor of 4 in temperature. And here you go nothing, right? 20, 30 degrees over 170, 300. So, and this comes from the fact that this DNA binding, it's really temperature dependent, right? It's delta G that controls it. So you can really condensate in a short temperature interval what you would need to this would be impossible to do an experiment on this time scale, right? For time temperature of your experiment, it's almost impossible. Okay. So good that we use DNA. Well, not easy. Okay, so the idea. We start to make sure that we have understood. We have all the isolated strands at the beginning, then we combine them, we form the nanostars. Nanostars are around 80 Celsius. Now we go around 50, and then we form our gel, and the blue and the red are still floating. With their short sequence, they don't bind. Entropy is to prevent them from binding. Now we go to lower temperature, and then they really want to bind, and then we have the isolated strands. So we increase from here to here, we go fluid, gel, fluid, at least in our minds. Let's see the experiment. First of all, the phase separation. So this is one specific density, a function of temperature. The sample is homogeneous over here. It starts to have a meniscus in this region here, and then it becomes again homogeneous in this other region there. You repeat this experiment at all densities, and then you mark the points which are phase separated, and you repeat the phase diagram. And what you see here is that you recover the re-entrance, that saffron-like re-entry that you also seen in the experiment. So that's a good sign. Now we can go in at this density over here, where the system is not phase separated. It's a perfect equilibrium gel. And we can cool it down. We start to go from high temperature to low temperature. And you see that the alpha relaxation time gets slower and slower, and the system goes above 10 seconds. Again, you cannot do experiments anymore. So for us, it's non-ergodic. So it's really a gel. And if you keep cooling down, you cannot do experiments. The correlation function does not decay in your experimental time window. So again, from 50 to 40, right? Roughly in this, until you go down to 25, so much lower temperature. And then you start to see the correlation function coming back. And you see that it becomes faster and faster, and again, it has the same time scale of the high temperature. So you put together all these points, the correlation, the alpha relaxation time gets slower and slower, and then goes well beyond what we can measure, and then comes back, becomes faster and faster. So we really have in the experiment to reproduce exactly the physics that we had in the simulations using these DNA particles. Sorry? Experiments are done. I want to go where? In Rome, by my postdoc. So the previous one, the phase diagram, was done by Tommaso Bellini in Milan. And then we learned from him, and this and the next will be in Rome. Always in collaboration with Tommaso, but fine. Okay, this is, we want to prove also the elastic properties. What does it mean, all this? Okay, we want also to check out the rheological properties of samples. Of course, those samples are really tiny, 20 microliters, so there is not much that we really do macroscopically. So you have to put a probe in it. But the good thing is that if you put a colloidal particle, let's say 400, 500 nanometer, sufficiently large that the scattering of these particles kills the scattering of the DNA. Yeah, because the samples are cost of the DNA. We use very pure DNA, and that's a rise. Probably we could use, but we don't dare. Even cheaper DNA. Then you're not, they don't guarantee that the length is always the same, that the sequence is always the same. It's a fractional mistake. So at the beginning, we don't want. In the future, probably we switch to the cheap one. But just to give you an idea, one of these experiments cost 2,000 euros of DNA. I mean, everything. I mean, first time you buy, you try it, you check it, and then or the order is not that bad. 2,000 euros. You think of 1 month of PhD or postdoc, right? They cost more. So you put the, this is what I try to tell to my students. Don't be afraid to buy the sample, because you cost me more. Because they're very scared to use it. Oh, I don't want to repeat, it's dangerous. Buy it, forget it. Okay, 10,000 I will not do it, but 1,000 it's okay. So we put particles, colloidal particles, in the sample, and those particles have a larger refractive index, so the scattering of those particles is dominant compared to the scattering of the DNA. Actually, it's not, I mean, the DNA doesn't scatter too much, so it's very easy. So you see only the scattering of the probe particle, even if you put very tiny amount of them. But let's say packing fraction 10 to the minus 4. This is the order of magnitude. So you really see the self-motion of those colloidal particles. You can measure the correlation function with the light, and essentially what you're looking at is the diffusion coefficient, the mean-square displacement of the particle. You're measuring the mean-square of the particle. You can invert the mean-square of the particle and get the elastic moduli, G prime and G double prime. And you see, again, the same trend on cooling. You start from a typical liquid-like behavior. Then we go to a case in which we have selected the temperature, in a case in which G prime is equal to the G double prime in a large frequency region, and that's a usual indication of a percolation transition. You have a cluster of all different sizes here. Then you go to almost a plateau, which is essentially a signature of an elastic behavior. This is the gel. Now the gel melts again to a percolation transition. Again, they become identical. And then you go to low temperature, and you get again the same type of behavior that you have at high temperature. So again, fluid, gel, fluid, through to percolation transition. Okay, now let's go to the last topic that I wanted to tell you about. This is more recent work, it's not completed yet. We wanted to do this, remember we discussed this idea of the V-trimers of a system which is in the ground state that's able to swap bonds. And of course, this can be done with the polymer, with this particular chemistry that has been invented by Ludwig Leber. But we would like to make a gel that is able to swap the bonds, also with just simply using DNA. So let me remind you what the idea is. You work with a binary mixture. In particular, we use nanostar of valence 4 and nanostars of valence 2. And of course, if you work a stoichiometric ratio, then the system is fully bonded at low temperature, and there are no free ends in the system. But if you work off stoichiometric, so you put a majority of particles with valence 2, then you get a reasonable number of free ends in the system. And we can use those free ends which are in the system to activate a swap mechanism. That's what we want to do. So those are our particles, particle with valence 4 and particle with valence 2. We mix them non-stoichiometric concentration, and we get, in principle, we should be able to design a swap method, a swap mechanism, and see these dynamics. Now, again, let's take, before doing it, let's decide what concentration we have to use. And again, the beauty here that we can again use the theory that we discussed 2 days ago, is Flory-Stockmeyer. We calculated all the cluster size distribution, the percolation probability, and all these quantities. And here I just show you, as a function of the relative concentration of the two particles, the number of particles which are in the infinite cluster. And I just blew up this part here with very large infinite cluster, particle in the infinite cluster. And you see here that if you work with this stoichiometric ratio, then all particles, and this is calculated assuming that all possible bonds are formed, really in the ground state. So you work with the packing size ratio 0.33, and of course all particles are in the infinite network. But if you go down to 0.28, then 96% of the particles are in the infinite network. And then if you work with the X25, then 90% of the particles are in the infinite network. So those typical numbers give us a reasonable number of free ends, But still, we have a strong network that can support stress in this case here. So essentially, what we are trying to do is, again, a fluid, gel fluid, but this time playing with the concentration, X. Okay, now we have to design this swap mechanism. And this is a beautiful work that Flavio did a few years ago. The idea is that those are the sequences. I don't want to discuss too much how it works. Again, he designed essentially the sticky sequence of the dimer of the bridge and the sticky sequence of the tetramer. And the idea is the following, that you start with this dimer which is connected to tetramers. And there are, the important point to understand is that there are these 4 bases, which we call toehold, here and here, which are free, where some other strands cannot touch. So now if there is a free end around, this free end cannot touch these 4 bases over there. So we can start the swap dynamics. So look what is happening here, and a new strand is coming, it's attaching here. And now if you design the sequence properly, that's the trick. Now, this sequence here can bind, and this one can evaporate at the same time. And this doesn't cost any energy, because you break one existing bond between 2 base pairs, and you create a new bond. So the energetic cost is very small. There will be, since there is a very small energetic cost, it's nothing more than a random walk in this sequence space. You all move back and forth in this space until at the end, or the first one evaporates, the incoming one, or the previous one evaporates. So here is the case in which the sequence, the new sequence have formed the bond, and the old one evaporates again. So there is some theoretical work in designing the sequences, but that's okay. I mean, I don't want to discuss too much that. This is a mechanism that is known in DNA nanotechnologies, called toehold-mediated strand displacement. The very nice idea that Flavio had was usually this toehold mechanism is one directional. You use it to swap, to change from one sequence to another sequence. This has been used in DNA workers. If you want to design some particles that walk on a carpet, then you use this type of toehold mechanism. The nice idea of Flavio was to add toehold on both sides in such a way, and designing the sequence in such a way that this works in both ways. So you can swap in both directions. The toehold. The idea is that the concept of the toehold is nothing more than to leave a certain number of bases where an incoming sequence cannot touch. And now, if this sequence here, the bases that you have here, are identical to those bases that you have there, apart from the first 4, then they can swap, but they do it one after the other. So the energetic cost of doing is very small. One evaporate, one fall. Yes, you want first that all you need that all that 4 or 5 bases because you want that to stick there, and then to swap. Exactly. Yes, well, there will be it's a random walk process. So at the end, you can or evaporate the incoming strand or evaporate the existing strand. If you evaporate the existing strands, then you swap the bonds, because this one is now bonded to that one. And this evaporates away. Maybe with this movie, you follow it a little better. So this is a simulation of this process. With simple DNA models. You see, this is the gel, and you don't see the gel, just focus on the tetramer and an incoming free end. So this free end now is attaching in the toehold. Now we will stay there for a while. We'll do this nice random walk. A little bit of time. And then at the very end, it evaporates, and the swap has taken place. So on the computer it works, right? Let's see on this in the lab. This is the system at concentration 3.3, almost done. It's Friday, it's nice, we want to go home. Actually, no, but some of us. So let's look at x equal 0.33. There are no, in principle, no free ends here. You lower the temperature, you form the gel. it becomes non-ergodic around 47 Celsius. So nothing different from what we've seen before. It's only taking place at a higher temperature because the sticky sequence is longer. But with no free ends, there is nothing that happens. And if you look at the alpha relaxation time and you plot it as a function of 1/t, you find a Arrhenius behavior for the alpha relaxation time, like we have seen already before. The slope of this alpha relaxation time is the activation energy of this number of bases that form the bond, so as it has to be. So everything is clear. So no swap phenomenon. There is no speed up that we see in this one. Now let's look at the sample with the X25, which we have seen that there are a lot of free ends. And now you see that even at 21 Celsius, this has not become as low as the previous one. So here there is really a speed up of the dynamics, significant speed up of the dynamics compared to the previous one. Let's look at the alpha relaxation time here. So, and this is the 28, is the red one. Now those are the one X0.33%, so no swap. It's Arrhenius. If you would continue this curve, of course you cannot do experiments. Here is months, years, and so on. But this one is given by this slope over here. You see how faster has become this system. It's not like the swap of Ludovic, but we have also gained 5 or 6 order of magnitude in speed up thanks to this swapping process in DNA. If you look here where you have the data at all 3 different concentrations, something that we cannot do here, you see here that really, as a function of the concentration, you have a speed up, a significant speed up of the dynamics. But it becomes a really incredible at very low temperature. Now, how can you control this? This is the slope of the 11 bases that we have put for the bond. And now this is then again an Arrhenius. At the end, this is the slope. The swap region, it's more complicated to describe the dynamic, but at the very end, the typical time scale is the evaporation of the toe hold. Right? The toe hold touch, does all the random walk, and then at the end it has to evaporate. And so the typical time that controls the swapping process is the evaporation of this bond. And so now this has a slope 4, and this has a slope 11. So we have not really created a detrimers because we have not been able to stop entirely the dynamics. We have a dynamic which still goes on, but a much faster scale due to the swap. But this is something that we are thinking how to do it, adding some capping of these toe positions, but the swapping phenomenon has been, I think, proved. Okay, so that's everything I wanted to tell you. We have using this DNA nanoparticle not for DNA nanotechnology approach, not to build really aggregate machines and things like that, like they do in a nanotechnology, but really to use it as a system that can be the experimental counterpart of all the strange ideas that you developed in a computational theoretical group. And we have seen some application to these cases here. I need to thank all the people with whom we have been collaborating, with whom we have done all this theoretical and numerical work. And there is an DNA origami that is going to self-assemble to thank you for these lectures. And if you have questions, so you can ask me whenever you want. Thank you.
Thanks a lot to Francesco for the 3 lectures. So if you have questions, please do ask now. We'll skip the tutorial, so please feel free to ask questions. We'll come to you, don't worry. Anybody has questions? Nobody has questions? Francesco, you are free now.
Perfect.
You have a question? Okay. One, the other. To ask? Yeah, of course, you are allowed to ask.
No, maybe I missed it, but I was curious to know what kind of applications you have in mind for this idea of starting from a fluid and creating a gel by heating. If any, I mean, maybe it's just, I don't know. I was curious.
We started just with as an idea, let's see if we can do it. Then now we have a small project which is just starting in a collaboration with some biologists, because the idea is that this gel, this material here is fluid at ambient temperature, and this gel at body temperature. So now you can inject easily this liquid in your body, and then immediately gels inside. And one of the real problems that apparently the people have is to inject drugs, because they're really viscous very often. And so if you can dilute them in the solution, when you inject, it becomes gel, you can concentrate in the place where you want, and then they very slowly will diffuse away. So they are trapped from the gel. So we are starting to look at the interaction between living cells and this type of materials. No, I don't believe in patents. That's why they don't like me.
Okay, more questions? No? So let's thank Francesco.